Assalamu alaikum, my name is Janbad and today my topic is design experiment to determine cell constant conductivity at 25 Celsius. Well, basically, we're not discussing the cell which is in human body, we're basically discussing about cell which is in chemistry. So it is an cell is basically an concentrated solution in which we found some salts that could collect electricity. So this is not basically a living cell, it is artificially made cell which conducts electricity. So here we have in specific temperature which is given 25 Celsius. So the best salt cell constant, or you can say cell, or you can say salt in a solution that can conduct uh, uh, cell constant at 25 Celsius is KCl. So we'll be considering KCl as the whole cell constant in the whole presentation. So let's start our presentation in the name of Allah, who is the most beneficial and merciful. So first of all, let's see the contents. So here we have cell constant, conductivity, effect of temperature on conductivity, designs and calculations. So we have a whole lot of bunch of things to study one by one. So let's get to the point and let's talk about cell constant first of all. So as I've already told you that this is not a human cell. Basically it is cell in chemistry, or clearly in electrochemistry. Chemistry is basically a solution or device which could pass electricity through it. As I've already told you about that this is not a living cell. It is basically a usually studied in chemistry or electrochemistry, which contains which can pass electricity through it. So this cell consists of anode and cathodes. Yeah, this cell may consist of anode or cathode. Well, to pass electricity, to perform some specific experiments, it also should contain anode and cathodes. This cell membrane contains solution which is made up of water and salts. Usually, as I have already told you, that mostly salts are considerably used, but at a specific 25 Celsius temperature, KCl is the best salt that can be used to perform this experiment. So the cell can also be connected to different types of meter in order to calculate different variants. So it could be ohm meter, it could be chart meter, it could be any type of meter which could be used to determine different. It could be these meters could be used to determine the resistance, either the current, either the flow of charges, anything. It could be anything. So it depends upon the meter that we have connected to, or the system, or the solution, or the cell. So it can also be connected to a circuit containing resistors for calculating cell resistance. As I've already told you about the resistance that we can also use to measure resistors about it. So basically there was cell. Now let's talk about cell constant. So the cell constant defined as K, corresponding to the theoretically electrode consisting of distance of 1 centimeter between 2 centimeters cube square plates. There are units of 1 centimeter for a cell constant, where the sum corresponds to the ratio of the distance between the electrodes plates and the plate surface area. The ratio of the distance between the cell electrodes and the areas of electrodes is determined by cell constant of a given cell. The cell constant is defined by the distance between the electrodes and the cross-sectional area A. It is measured by calculating resistance of the cell containing a known conductivity solution. So basically cell constant, which is also written as K, is basically the distance between two square plates in a solution, in which we basically usually you can say this between two electrodes, which has a cross sectional area of A. So it basically is the basic definition of cell constant is the distance between two electrodes. We have to remember that, and the area between them is a cross sectional area, so it is represented by A. So we should keep this thing in our mind whenever we hear about cell constant. So this is the perfect definition of cell constant, that the distance between two electrode is the proper definition of cell constant, and the area between these two electrodes, which is cross sectional area, and that cross sectional area is represented by A. This is the proper definition of cell constant. So before heading towards anything, I should give you the basic overviews of everything. So before going forward, some of us maybe really would have not known the meaning of conductivity. So let's talk about conductivity, and basically, and its reciprocal is resistivity. So I'm gonna explain them bothly. I just give an overview because this is not my topic, but I just have to give an overview of it to go further, as it is an important. It relates too much to my topic that I have to explain it uh, overviewly. So conductivity is basically the ability of a material to conduct electricity or heat. So basically, conductivity is the characteristic of a specific material that it conducts electricity, a specific amount of electricity or heat. Well, every element has its own conductance, as I've written in the second points. Every substance has its own conductance. Reciprocal of conductivity is resistivity. Like resistivity is the force that stops or that conductance of electricity or heat. Well, similarly, it is same with resistivity, that each material has its own amount of resistivity for different like for heat and electricity. So it has a greater role in cell constant, and it is derived with kappa, which is called cell constant of as we know that the kappa is the cell constant, the real cell constant, which is k, which is written in equations and will be used quite variably in our calculations. So in that way, conductivity relates too much to cell constant. So let's move on to the effect of temperature on conductivity and resistivity. So basically, what does we've given a 25 Celsius temperature, which was quite rarely be matched to the room temperature, because if it will be 60 Celsius, that would be hard for me to determine. But and even if it was lower than 5 to 0 Celsius, so then it would have also been hard for me to measure and search for that. But at 25 Celsius, it's almost a room temperature, so it wasn't so hard for me to describe and calculate the calculations to understand the meanings of other things. So I think I'm quite lucky that I got 25 Celsius. I don't know about other people. I don't know about the other people. So let's talk about that what does temperature has an effect on conductivity and resistivity. So temperature has a great impact on conductivity. Let's clear this, that there is no change in conductivity in low temperature, as it does not affect the electrons in atoms. So basically there is an different situations in low temperatures and high temperature. As in high temperatures, the electrons which are in a cable of a wire which conduct electricity starts to vibrate with each other. In high temperature, I'm talking about high temperature, they start to vibrate with each other, providing the moving the electron which takes the current, which moves the current, to provide a very small surface that it can't even move from there. So that provides that electron quite a favorable condition to move. So in this way, high temperature makes a great bad impact on the conductivity of heat, whereas in and low temperature, whereas in on low temperature it does not affect that much, because the electrons remains simple, and they do not usually get free, so that's not a mess for them. So but we will operate our design at calculation 25 Celsius, at which free electrons work perfectly. So this was a design that I made myself by searching, because I had to work for this, so I didn't found any pictures already made it on Google's or anywhere. So I had to design it myself, but I was out of pixels, so I couldn't work on my laptop because it has some problems with it. So I couldn't design it. So I wrote it by myself and printed on it. So here, as we can see, that at the left side and the glass, we have a water solution having two electrodes, and the solution has KCl, which perfectly works on 25 Celsius. And here we have an and a Wheatstone bridge which has two resistors and about 3 points A, B, C, and which are interlinked with each other, so we can determine the resistivity of each by the help of kappa, which is the main cell constant of this process. So here I've written that 25 degrees Celsius, the specific conductance of our normal solution of KCl is 0.0027 65 ohm inverse. The resistance of cell is 40 ohms. The cell constant is, we have to find the cell constant. It is your L upon L AL. It is your length and it is your area. If you see that it is in centimeter in area, will be centimeter, L will be a centimeter square foot, means it comes out to be centimeter was, so now also could be initiated and was written to be no resistor, which is equal to help on we have given in the question that you have under 14 ohms and your specific conductance noted by OK. The copper is equal to 0.02765. So as we can see, specific conduction, so here we can see that kappa is the only kappa is determines the cell constant, whereas when electricity moves through it, the electricity from both of these electrodes move towards this Wheatstone bridge, and half of it moves through the M, then after the resistor, and after the resistor we get that we have two resistors. So that means that A, B, these are 2 points which are interlinked with AC and BC, which is equal to BC. If we write it directly that AC is directly proportional to CB or BC, and then we can also write it that AB is interlinked with each other, which is also equal to MRX, and BRX is also interlinked with MBR. So this is a great relation between each other, which tells us about the relation of cell constant with each other. So next, there is another point written here, specific conductance. So it means we have to reverse it is 1 of our 1 upon, which is 1 upon, so I can substitute one of these couples. So in this, so this is the whole process that I've already explained you in short form, so I don't think so that you'll understand like this. So I'll have to show you the calculations that I've written in here. So basically at 25 Celsius, the specific conductance of KCl, which is an cell, is 0.0276 microcentimeter per micro per centimeter. Cell has a resistance of 40 ohm. It is cell constant will be D. So we will determine the cell constant. So basically D is representing cell constant. So if we write B is equal to L over A, L is the length and A is the cross sectional area. If we measure and maintain the units right here, for example L over A, we are seeing bottom down of the page. So LA, if we see that L is equal to centimeter, whereas area is equal to centimeter square, so the centimeter square on the centimeter will cancel up with the upper centimeter, and then we'll have per centimeter. So this per centimeter is its unit. Now let's find out its cell constant. So its constant, before starting to find the constant, so R is equal to rho is equal to L over A. We can also write it as B, but we'll write it L over A to demonstrate it, and write it in more equality and more definition. So let's talk about what are the values that we have in our possession. So where resistance is 40 ohm, and let's talk about, and kappa is the constant which can be replaced by 1 over P, and its value is K is equal to 0.02765 ohm per centimeter. So kappa is the constant that is used in cell constants. So to make 1 over P, we will also make R 1 over we also have to make R into 1 over R. So 1 over r is equal to 1 over rho and L over A. Now we will replace 1 over rho into kappa, like I've already written here that now by rearranging it, like 1 over p is already converted in kappa, and 1 over r is equal, then 1 over r is equal to kappa over La. Now if we rearrange everything in this equation, so we will have La is equal to k into r, and La can be also be written as B, which is cell constant. So cell constant is equal to kr, where k is the kappa, which is the constant of cell constant, and r is the resistivity. So in this way, I've already told you that resistivity has a great role in our resistivity, and conductivity has a great role with cell constant. So this is the relation that I was telling you in the beginning of the presentation, that resistivity and conductivity has a great role in our great role in cell constant, and kappa is the constant. Basically it will appear no matter whatever happens, and B is the symbol that represents cell constant. It can also be written as length over A if we use it, if we see its meters. So centimeter over centimeter square comes, but the square cuts the centimeter above, so it becomes inverse centimeter. So by using this we can find cell constant at a specific temperature, but this is at 25 Celsius, because it's almost room temperature, so it is not required to be worried about anything. You can also find it till 20 to 40 Celsius, because these are relatable to room temperatures. So these are the conclusions that after finding and studying this all of the cell constant, I found this. Usually the cell constant is calculated by calculating the resistance of a solution containing a cell whose conductivity is already defined. We will use KCl solution for this reason, whose conductivity is correctly known at different concentration and different temperature. So basically I've already told you that KCl is one of those solutions whose conductivity and resistivity is already known at different concentrations and different temperatures. So cell constant is and as I've already told you this, that cell constant is also used to calculate the resistance of the solution. Well, I didn't told you this, but now it is a part of conclusion that resistance and conductivity is used to calculate the resistance of a solution. So basically the next point that met our conclusion, the ratio of distance between the cell electrons and the area of electron is determined by cell constant of one given. The cell constant is defined by the distance between the electrons and their cross sectional area. So basically this was the simple conclusion, but I've also already simplified it by telling you that basically the two electrons, and cell has two electrodes, the distance between them is basically the cell constant. There is nothing more to just take a headache on it, but there are two electrodes, and the distance between those electrodes is cell constant, and the area which cross sects them each other is called cross sectional area. So the third and the last conclusion that we have is, it is measured by calculating the resistance of cell containing a non-conductivity solution. So basically if we know the resistance of a cell, we can calculate its cell constant. So this is a really important point, that if we know the conductivity or the resistance of a solution, we can find it, because if we know the resistivity, we can find the distance between the electrodes, we can find the cross sectional area of the final. But the resistivity is very important, because it's in quite big process to find resistivity of some material and some substances. So this was my presentation. If you have any confusion, you can ask me on this in the comment section, and hope you guys enjoyed my presentation, and this was it, and hope you guys enjoyed it, and take care. Allah Hafiz.